we started simple harmonic motion. Simple harmonic motion is the core topic of this chapter. Even this chapter is actually oscillation, but it is famous in the name of SHM. SHM is a type of oscillation in which the displacement from the mean position is directly proportional to the acceleration and is always directed towards the mean position. I think we had copied this.
Yes, sir, we did.
A is equal to minus omega square, and omega is a constant, keeping omega constant, and then A will be proportional to minus F. This is a small derivation. So we are keeping omega constant. Copy this small derivation.
Done, sir.
Now, oscillation is a periodic motion. Oscillation is a periodic motion, which means it repeats itself this is oscillation, and you will notice that it is moving with the same amplitude. Now I'm going to increase the resistance to oscillation. Carefully see, the amplitude is decreasing. I'm increasing the length. When you increase the length of a pendulum, its time period also increases. Increase the mass. You can notice that these are the main factors.
The maximum displacement of a body is the point at which it has maximum acceleration, which then decreases as the body is approaching the equilibrium position. The acceleration is always directed towards the equilibrium position. The maximum displacement of a body is the point at which it has maximum acceleration, which then decreases as the body is approaching the equilibrium position. The acceleration is always directed towards the equilibrium position. The maximum displacement of a body.
Now, I repeated this, and this is a very important concept, that when an object is doing SHM, its acceleration is proportional to negative x. Negative x means that the resultant force is always directed towards the mean position.
Let us consider the oscillations of a pendulum as it moves along line x around the equilibrium position 0. When the movement takes place along a section from the equilibrium position to the point of maximum displacement, the acceleration vector will be in the opposite direction to the velocity vector. This motion is called decelerating motion. When the movement takes place along a segment from the position of maximum displacement to the equilibrium position, the acceleration vector will be in the same direction as the velocity vector. This motion is called accelerating motion. So the instantaneous acceleration is always directed towards the equilibrium position, and its magnitude is always proportional to the displacement. Let us consider the oscillations of a pendulum as it moves along line x around the equilibrium position 0. When the movement takes place along a section from the equilibrium position to the point of maximum displacement, the acceleration vector will be in the opposite direction to the velocity vector. This motion is called decelerating motion. When the movement takes place along a segment from the position of maximum displacement to the equilibrium position, the acceleration vector will be in the same direction as the velocity vector. This motion is called accelerating motion. So the instantaneous acceleration is always directed towards the equilibrium position, and its magnitude is always proportional to the displacement. Let us consider the oscillation.
So this is a very technical level concept that during a simple harmonic motion, acceleration is always directly proportional to minus x. Acceleration is directly proportional to negative x. Now give the heading examples of SHM. Now make this concept again that SHM is a type of oscillation, any oscillation in which acceleration is proportional to negative of x, it means it is an SHM. So this is a very important concept to understand. The simple harmonic motion is a special type. It's a special type of oscillation. So first you should recall and strengthen this concept that actual topic is oscillation. During oscillation, acceleration is proportional to minus x. It's a special condition. What it means that acceleration is proportional to the displacement from the mean position, what the negative sign is showing, and the negative sign shows acceleration always directed towards the mean position. So one of the most difficult concept of this chapter, that what is the meaning of the term acceleration is directly proportional to negative x. It means as you go away from the mean position, your velocity will change more rapidly until you stop. And then you come back. When you go towards the mean position, again you are going closer to the mean position. At the mean position, velocity will be maximum. This is a first concept. Secondly, what's a negative sign is showing that acceleration is always directed towards the mean position. Now you have to copy this.
Yes, sir.
The main heading was examples of SHM. Now give the heading simple pendulum.
Done, sir.
Now this is a simple pendulum which is swinging, in between two extremes. The pendulum is swinging at a constant rate, assuming there is no friction. Now this is a simple pendulum. It's hanging and it will be moving. The tension is upward in the string and the weight is downward, which is mg. Initially, the two forces are equal. So after giving the heading, you have to copy this.
Done, sir.
Now let's move the pendulum. Give it an impulse, as I was showing you in an animation. Give it an impulse and it will begin to move. When it reaches a new position, I'm using AS physics, the mg will make an angle theta. So I can resolve it, when you find a vector in a new position, you can resolve it mg cos theta, mg sin theta. Now you have to copy this. So can you recall for me how this resolution is made?
It depends on the horizontal and vertical axis.
Very good. And
Uh,
how we decide where is cos, where is sine?
the sine is the vertical axis,
No,
and
angle. Where you
oh,
mark the angle.
that
That
is your cos. The line where it's meeting the angle, that's the cos.
yes. So write under it that assuming assume there is no assume there is no resistance to oscillation. There is no resistance to oscillation, comma, pendulum is swinging freely this is an assumption, and I had shown you in an animation that if friction is there, the pendulum will eventually come to rest quickly. Now, can you recall for me how we used to make equations from this position, this point?
I think you can equate it like you can take mg and you can equate it to one of the components.
Which force is facing mg cos theta?
Uh, is it sine theta?
Good. Mg cos theta. Make it clear again. Look at the
Oh,
facing forces.
oh,
Mg
is it?
sin theta is not facing. Mg sin theta is unbalanced.
Yeah, yeah. And it's facing the tension. It's opposing the tension.
Mg cos theta is facing the tension. Acha, I ask again. Mg cos theta is facing the tension. What about mg sin theta? Is it unbalanced? Mg sin theta is unbalanced. So when it is unbalanced, will it become the resultant force?
Yeah.
And resultant force is always equal to ma. Specially notice that there is a negative sign I have inserted because of the nature of SHM. You have to copy this.
Done, sir.
For derivations in our A2 or AS, we always take assumptions, and it's always a series of assumptions. So look at this assumption that I have taken a separation X. The angle theta is very small, as pendulums do not swing on very large separations. X is very small, theta is very small. So you have to copy now this screen.
Done, sir.
Good. We can make a triangle. If theta is very small and you are using a radian function, it's a mathematics concept, then sine theta is approximately equal to theta. So the values are nearly the same. So we'll make a right angle triangle, we make an identity, and we will make this relation that sine theta is opposite upon hypotenuse. So now copy this screen.
Done, sir.
So now A is equal to, our first equation was A is equal to minus G sine theta. Now I can replace sine theta by x upon L. And for simple harmonic motion, A is always equal to minus omega square. So I'm going to compare it. You have to copy these steps of derivation also.
Done, sir.
Now, if I compare it, I will get a minus cancellation and I will get the formula for time period. T is equal to 2 pi under root L upon G. You have to copy this screen. I'm just coming. I have to say Asar Namaz. So I'm just coming. Copy this screen. Now give us side heading, evidence of SHM. A is equal to minus G sine theta upon X. If we use this approach, A is equal to minus GX upon L. And remember this main idea, how we prove that something is SHM, we have to prove that acceleration is proportional to minus X. Whenever you want to prove that something is SHM, you have to prove this equation. If you get this equation, if you get this equation for any motion, then it will be SHM. I repeat, SHM is a special type of oscillation. So if you prove that A is proportional to minus X, then it will be a simple harmonic motion. Now, give a heading, evidence of SHM, and copy this screen.
That's a
The important thing, which I said, the most important difficult concept of this chapter, the most difficult concept of this chapter is the idea that when something is oscillating, the acceleration is always directed towards the mean position. Now, this is a very technical concept. It means that when something is moving in a circle, when something is moving in SHM mode, acceleration is always directed towards the mean position. I share with you a very short animation on WhatsApp because it's not working here somehow. So you have to look at this very nice understanding concept that acceleration in SHM. What happens in SHM? The acceleration is always directed towards the mean position. Have you seen it?
1 second, sir, I'm opening.
Is it working on your WhatsApp?
Yes, sir, I just saw it's working.
Good. Object moving in a circle. This is a rare topic. It comes very less. Give the heading, object moving in a circle. Look at this mirror, which is on the diameter of a circle. There is a mirror on the diameter of a circle, and an object is moving on the circumference. You can notice that when the object moves on the circumference, the shadow of the object moves the shadow of the object moves forward and backward on the diameter. This is a very interesting and rare type of simple harmonic motion where the shadow is moving on the diameter. Look at this animation. Now, after giving the heading, you have to copy this screen.
Then
Then copy this.
Done.
Loaded vertical spring. Copy this.
Done, sir.
Now look at this position, unstretched spring. You put some load, the spring stretches. Then you pull it down and release. It's a position of Hooke's law, and the object is in a state of equilibrium. Now the spring is gently pulled further down and released. It will begin to oscillate like this. Oscillation is a very important tool. That is why animation started with a musical background.
The mass hanging on the end of this spring is in its rest or equilibrium position. In this equilibrium position, the downward force of gravity is balanced by the upward force of the spring. The force of gravity or weight is always the same. As the mass is pulled downward, the upward force of the spring becomes greater than the downward force of the mass. This causes a net upward force. When the mass passes through its equilibrium position, the two vectors cancel out, leaving no net force acting on the mass. The mass has stopped moving at the highest position of its motion. At this point, there is a net downward force. Recall Newton's second law, F equals ma. At this position, the mass experiences a net upward force, which results in acceleration upwards. As this is position with the greatest upward force, this is the point of maximum upward acceleration. When there is no net force on the mass, it has no acceleration. The velocity is at its maximum here. Here there is a net downward force and the mass is accelerated downward. The velocity is 0. This is simple harmonic motion. 1. The acceleration is always directed toward the rest position. 2. The acceleration increases as the mass moves away from the rest position. Hooke's law, F equals negative kx, describes the force exerted by a spring. The force is a restoring force. The negative sign indicates that the force is directed opposite the direction of motion. The spring constant is k, and the distance from the rest point is x. When the mass is at the lowest point in its oscillation cycle, two forces act on it: an upward force, F equals kx, and a downward force, F equals mg. The difference between the forces is the net force kx minus mg. Here the spring force kx is greater than the gravitational force mg. Here the net force is ma, and it causes upward acceleration. At the top position, the spring force kx is smaller than the gravitational force mg. The difference is the force minus ma, which causes the mass to accelerate downward. If the spring is stretched 15 centimeters by a 45-gram mass, what is the spring constant K of the spring? A. 2.9 newtons per meter. B. 2.9 newtons. C. 2,900 newtons per meter. D.
Now, this was a detailed animation showing all the features when a loaded spring is moving vertically. This is the diagram. Now, when you release it further from the lowest position, what will happen that already there is an extension. E. So you should notice here E plus X. Why it is E plus X? The first extension is here. When you stretch it and leave, then this is the displacement from the mean position. E is the extension when the spring is loaded, and X is the separation from the mean position when the loaded object is moving up and down. So there is a contrast between E and X. That is why W is greater than T1. So after giving the heading, you have to copy this diagram.
Done, sir.
The extreme right diagram is actually showing the oscillation. The extreme right diagram update the same screen.
Done, sir.
W is greater than T1 and W minus T1, mg minus T1. Hooke's law is coming. Note specially X plus E.
Done.
So can you understand why I am taking W is greater than T1? Because it's going downward at this position. Why it is X plus E? Can you tell me why it is X plus E?
Because X is the difference from the mean position, how much it have extended.
Yes. And it is an addition. When it is in the initial position, mg is equal to ke.
Done, sir.
Now, remember that when I extend it, resultant force is equal to mg minus kx plus e. I have replaced, and now I'm replacing mg by ke. I hope you remember k is the spring constant. So continue the derivation.
Done, sir.
And then you make the subject a is equal to minus k upon mx. Now a acceleration is minus omega square. You always find this step because it's a fundamental equation. Compare it and find the value of omega and then t. So copy this derivation.
Done, sir.
Evidence of SHM. Give the heading.
Done, sir.
ME is equal to minus K upon M. Remember that. If you prove that A is proportional to minus X, then you can prove it is SHM.
Done.
Horizontal oscillation of a mass.
Done, sir.
Look, this is the horizontal motion. I have placed a block and it is attached with the spring. Now, if I slightly move it backward and release, it will oscillate forward and backward. You have to copy this. we will release this object from the mean position.
Done.
So when you extend it, there will be an extension. And when it goes inward, it will be E minus X. And when it goes outward, it will be E plus X. This is a very technical concept that the spring already have some extension. So you have to copy this. Have you copied it?
Just 1 minute. Sir. Done, sir.
So we keep it up to here, and we will inshallah continue this in our next class. Allah Hafiz.
Thank you, sir. Allah Hafiz.